Okay, so in this video we're going to look at what happens when a capacitor discharges through a resistor. There's a tiny bit of maths in it which is not on the syllabus, but if you do maths A level it shouldn't be too much of a challenge for you. So here we go, we've got a circuit with a capacitor in it, and the capacitor's been charged up to some voltage or other, and what we're going to do is discharge that capacitor through a resistor. So there's nothing else in the circuit apart from the capacitor and the resistor, and we can put an ammeter in there to measure the current, but that won't actually affect the circuit really in any way. And we can also add a voltmeter as well to monitor the voltage across the capacitor. So the idea is to combine together a bunch of different equations to derive the behaviour of this system. So there's lots of places we can start, but for this one we're going to start with current. Now, if we've got a load of charge built up on the plates of this capacitor, then when a complete circuit is made with this resistor, current is going to flow in the circuit. And as current flows, the amount of charge Q stored on the capacitor is going to decrease, because electrons are going to flow around. There we go, move that one back there. Electrons are going to flow around the circuit and neutralize positive charges over here, thusly diminishing the amount of charge that remains on the capacitor. So the amount of charge on the capacitor is going to go down. The current flowing, I, and if I just make this obviously an I for you, the current flowing in the circuit is going to be the rate of decrease of charge stored on the capacitor. So over here I've got a delta Q over delta T. That's the rate that the charge on the capacitor is going down. So as the charge on the capacitor goes down, it's going down because electrons are flowing around the circuit and then cancelling out positive charges on the other side. So there's a minus sign here to show that when we've got a current flowing, there's a negative rate of change of charge on the capacitor, so the amount of charge on the capacitor is going down. And the faster that charge goes down, the greater the current. So that's the first equation. We can also come up with another equation for current for this circuit, just using Ohm's law being V equals IR. We can just rearrange that to I equals V over R, where V is the voltage driving the current. In that case it's going to be the voltage across the capacitor, and R is the resistance in the circuit, and that's basically provided by the resistor here. The resistance of everything else in this circuit is really small. So we've got two expressions for current, which in a minute we can join together. But first I'm going to add in another equation, V equals Q over C, which comes from the capacitor equation Q equals CV, or C equals V over Q, depending on which way you have it memorized. So we've got another expression for voltage, and what I want to do is substitute this into here to get rid of this V, to get a new expression for current. And when we do that, we get I current equals Q on RC. So we've just replaced the V with Q over C. So now we've got two expressions for current, this one here and this one here, so we can equate those two things to each other, and when we do that we just get minus delta Q over delta T equals Q on RC. And for the sake of tidiness and reasons which will become clear in a minute, I'm just going to quickly move the minus sign to get this. So delta Q over delta T equals minus Q on RC. Now as far as the syllabus goes, that's where the story ends. But if you do maths A level, you might recognise this as almost being a differential equation. So if I replace those deltas by what they really should be, which is d's, we get dq by dt equals minus q on RC. Now if you don't do maths, you do not need to follow this in any way, shape or form, okay, but if you do, it's nice to look at. Now this q changes, okay, q changes, the charge on the capacitor changes. Over time the charge on the capacitor diminishes, so q is a function of time. The resistance and the capacitance are not functions of time, they're constants for this system. Okay, so we've got a differential equation, dq by dt equals minus q on RC. Now, I don't know how you go about solving differential equations in maths, but this is one that basically once you've got the hang of it, you can just solve by inspection. So you can just look at it and think, well, what when I differentiate it gives me back the same thing multiplied by, whoops, it didn't really shake the bit I wanted to, multiplied by just some constant, which is this minus 1 on RC bit. What when differentiated gives itself times a constant? That would be an exponential function. So if we try some sort of solution like let q of t equal q naught, some initial charge, e to the minus t on, whoops, what on earth am I doing? Q naught e to the minus t on RC I meant to write, sorry about that. Let's just give this a go as a solution. This should probably work. If I differentiate both sides, then dq by dt is going to equal, have a look at the exponent up here, multiplied by the derivative of that, so minus 1 on RC q naught e to the minus t on RC. Now this bit here is none other than qt, so this is minus q over RC, which is exactly what we wanted. That's what we were trying to show in the first place up here. So we found a function that when you differentiate it, it gives itself times minus 1 over RC. So this here is going to be our function for charge as a function of time. So you need to know this. You do not certainly need to know the derivation of it, but that just shows you where it comes from. So this you do need to know. Q equals Q naught e to the minus t on RC, from which we can think about what this is going to behave like. Essentially, once the capacitor starts to discharge through the resistor, we've got an exponential decay, because we've got e to the minus t times some constant. Okay, that should look a lot like radioactive decay to you as well. So what we're going to have is a lovely exponential decay of charge where it starts off at q naught. Now this exponential decay has a property, much like when we think about radioactive decay, we think about a half-life. Here we're not going to think of a half-life, we're going to think of a 1 on E life, but it's the same idea. So RC is called the time constant, and that is defined as the time it takes for the charge to fall to 1 on E of its original value, which is 0.37. So it's not quite the same as half-life, but it's a very similar idea. So if you read off the time it takes for the charge to fall to 0.37 of its original value, this time will be RC, the time constant. So lots of parallels with radioactive decay here. The maths is very similar. Now from this we can also just very, very rapidly derive 3 other expressions which are basically the same thing. If we note that Q equals CV and that C, capacitance, is constant in any given circuit, then the voltage will also display this exact same type of behaviour. So if the charge undergoes an exponential decay, then the voltage also undergoes an exponential decay, because the capacitance is just a constant. So we get a similar formula, V equals V naught e to the minus t on RC. Well, V equals IR, Ohm's law. R is just some constant. So if V decays exponentially, then I, current, is also going to decay exponentially. So we can also have this formula, I equals I naught e to the minus t on RC. So basically all of these quantities, when a capacitor discharges through a resistor, will display an exponential decay, and they'll all have the property that the value falls to 0.37 of its original value in a time RC. So, what's the point of all this? Well, as well as storing energy, which we talked about in a previous video, capacitors are used for timing applications. So you can use capacitors either directly to time stuff or indirectly within circuits for timing functionality. So, let's say a student wants to know how long the impact of a ball with a table lasts for. Maybe they want to calculate the average force that the ball experiences from the table or something like that. So what they've got is a ball that bounces on a table. They want to know how long the impact itself lasts for. Well, they could use a capacitor circuit for that. So for the circuit, what we've got is a battery. This isn't too good, is it? Battery here, capacitor here with a voltmeter across it, and a fixed resistor here. We've got some foil stuck onto something conductive stuck onto the ball, and something conductive stuck to the table, another bit of foil, and this is called a flying lead. Basically a lead that is flexible and can be attached to different stuff. So what the student's going to do is use the flying lead first of all to charge up the capacitor to whatever the voltage is of the supply. Then once the capacitor's charged, they're going to connect the flying lead to the foil on the ball. Then they're going to drop the ball and let the ball bounce on the foil at the bottom, and then catch it hopefully after it's bounced once. Now when the foil is in contact down here, just for the very brief duration of the impact, okay, the flying lead is still attached, then we've got a complete circuit for the capacitor to discharge. So the capacitor is going to start discharging through the resistor, but that's not going to last long, because then the ball bounces back up, okay, the flying lead is still attached, obviously. That'll do. However, the voltage across the capacitor will have gone down, because the capacitor will have discharged somewhat. So if the student has a capacitance of, let's say, 47 microfarads, resistance of 220 ohms, an initial voltage from the supply of 3 volts, and then they measure the voltage after the bounce as 2.1 volts, can we work out how much time the ball was in contact with the table for? The answer should hopefully be yes. We have our formula, V equals V naught e to the minus t on RC, and we want to know t, the time. So it's going to involve a bit of maths, but it will be familiar from radioactive decay, and it's just good practice. So V on V naught is going to be e to the minus t on RC. What we can now do to both sides is take the natural log of both sides. That's going to sort out this e to the minus thing here. Okay, so if we do ln V on V naught, that's going to equal minus t on RC. Then if we want t, we've just got to take the RC over the other side, RC ln V on V naught, and also take the minus sign over as well, and that should be that. So it's going to be minus 220 times, is it 47 micro 47 times 10 to the minus 6 times ln of V 2.1 over V naught initial 3. And with any luck, we can chuck that in a calculator and get the right answer. So let's give this a whirl. Minus 220 times 47 times 10 to the minus 6 times ln of 2.1 over 3 equals 3.7, let's call it, times 10 to the minus 3 seconds, 3.7 milliseconds. So there we go, with a really simple circuit, nothing special involved at all, just a standard capacitor, a standard resistor, a couple of cells. A student has managed to time how long it takes for a ball to be in contact with the table when it bounces. Pretty neat. Pretty typical application of capacitors for timing. So I've got one more question for you. This one's one for you to have a go at. So do have a good go at it and then have a look at the solution. In fact, this video is probably getting on a bit, so why don't you have a go at this and then I will go through the answer tomorrow in our lesson. So a 560 microfarad capacitor is charged to 5.5 volts and then discharged through a resistor, and initially a current of 5 milliamps flows. So what's the resistance of the resistor if initially the voltage is 5.5 volts and the current is 10 milliamps, and then how long will it take for the current to decrease to 5 milliamps? Have a go at that one, bring the answers to next lesson and we will see what you've come up with.